We just recently talked about translational equilibrium, where the sum of forces is equal to 0. But if we have an object that is not accelerating linearly, so in the x or y direction, there's no angular acceleration, then the sum of forces equals 0 and the sum of torque equals 0. And in this situation, we call this static equilibrium. Now, your first condition of equilibrium is that the net force is equal to 0. That means that your up force and your down force are equal to each other, and your left force and your right force are equal to each other. Your second condition of equilibrium is that your net torque is equal to 0. So those are the two conditions for static equilibrium. And what that means is that your clockwise torque is equal to your counterclockwise torque. So everything ends up needing to be balanced. And so in this type of situation here, in the situation where you have a hanging sign, it's important for your torque to be equal to 0 and your sum of forces to be equal to 0 in order for that sign to stay hanging. Okay. Another example is this is a scale that we can use in the science lab. And so if I was trying to find the mass of a bag of sugar or of a cube of sugar, this is called a triple beam balance. And what we would do is we would slide different masses. Okay. And when you slide the different masses go to a certain distance. And here's your pivot point right here where your orange arrow is. And once everything lines up and it's balanced, then that tells you what the mass is of the sugar, because what's on the right hand side is equal to what's on the left hand side. So these forces right here, or these masses, are going to be pushing down to the right. And then the sugar is going to be kind of rotating your balance counterclockwise. Okay. So in this case, we see that the sugar is equal to 200 plus 100 plus 50. So it looks like 350 grams in that case. Okay, so there's some things to consider when you're doing these problems in this unit is that your torque, what is your torque equal to? Your torque is equal to your lever arm being your perpendicular radius to your force. So that's equal to the radius from the axis to the force times sine theta, or you can remove the sine theta altogether and just say that it's the perpendicular radius or distance from the point of rotation to the force. Also, something to remember is we know that sum of forces equals mass times acceleration when we're talking about translational forces. In this case, when we're talking about rotational, we have your angular acceleration is equal to the sum of torque, or the net torque, divided by your rotational inertia. Okay. And then also your force of gravity is always going to act at the center of mass. If a force acts at its axis, then your torque is equal to 0 for that force. And then you can choose whatever axis of rotation you want to choose. So I included this diagram here. And the reason I included this, this picture, is because I want you to see that we have a lot of forces going on here. So here we have a force being right here that's pushing down on this. Okay. And then you have this pivot right here, that pivot point. And then you have a force that's pushing down that way. And that's going to cause this torque that way. And then your rotational motion that way. And the same thing on this side. Okay. So we have these different forces. Okay. Now that force going down, then we look at this platform and that we have our tension force. Okay. We have another tension force. Then we have the force of this person right here, the force of that person right here, and then the force of the board right there. Okay. And in this case, you could have a pivot point right here, maybe. Okay. So I would choose my axis of rotation here. So then I'm only taking into consideration this torque, that torque, that torque, and that torque. Okay. And we're going to look at different examples, but this is a perfect example of something that is at static equilibrium. So let's just dive into some of these questions. Here we have an in-class experiment. Students hang heavy masses from a 2 kilogram rod and attempt to balance it on a pivot point under its center. Okay. If a 5 kilogram mass is hung on the rod at a distance of 23 centimeters from the center, where should the 7.2 kilogram mass be hung on the other side to balance the rod? So we have our rod, okay, and we have our pivot is at our center. Okay. So at that point, that's where your weight of the rod is going to be. So in this case, we're not going to look at that as adding our, or that's not going to add to our torque. So we have a 5 kilogram mass is hung at a distance of 23 centimeters. So we'll say 0.23 meters. And that's going to be that mass, and it's going to be 5 kilograms. So 5 kilograms times gravity. Okay, and then we have a 7.2 kilogram mass. Times gravity. And we're trying to figure out what X is in this situation, okay? And again, it doesn't matter how long the rod is in this case, because we know that the mass of the rod is right down here. So that's not going to add to the torque. I know that my sum of forces in my X equals 0. My sum of forces in my Y equals 0. And my torque, my sum of torque equals 0. Okay. Then when I look at this, okay, what is my torque? Well, I have my torque here. That's going to be clockwise. And then this torque is going to be counterclockwise. So I end up having, I'm going to just look at my torques here. Okay. So my sum of my torques is equal to 5G times 0.23 minus, because it's the opposite direction, so counterclockwise, 7.2 GX. Okay, and that's going to equal 0. So we end up having 5G.23 equals 7.2 GX. Now notice my G cancels here, and I end up getting that my X value is going to be 0.16 meters or 16 centimeters from the pivot point. Okay. So let's look at another problem. And this is like that scaffold that I showed you in that picture. A man is standing on a scaffold supported by 2 vertical ropes, one on each end. The scaffold weighs 150 newtons and is 2 meters long. What is the tension in each rope when the 600 Newton man stands 0.5 meters from the right end of the scaffold? Now, these problems are impossible to do if you do not draw them out. So here I have my scaffold. And my scaffold is 2 meters long. And it says 2 vertical ropes on each end. So on each end, I have tension. I'll call that tension right. And I have tension left. Okay. And then at my 1 meter point, I have my mass times gravity, or my weight, which is 150 newtons. And then I have a 600 Newton man. Okay. And that 600 Newton man is at 0.5 meters. Okay. So then the next thing that I'm going to do is I'm going to look at my forces in this case. So it says, what is the tension in each rope when the 600 Newton man stands 0.5 meters from the end? So I know that my sum of torque equals 0. Okay, so I know that my sum of torque is also equal to, first I need to choose what my pivot point is going to be. Okay, I'm going to look at that and I'm going to say, okay, well, I'm going to make this my tension left as my pivot. So what I mean by that is if I keep this rope here, if I cut this rope right there, it's going to pivot along that point where the tension on the left, that left rope, is kind of holding on to that scaffold. Okay. You can imagine that if you've ever seen two things hanging and you cut something, if you like looked at the lights on the top of my ceiling in my classroom and you cut the cords hanging them from the ceiling, but you left one, and then that light is going to swing on the one that's still hanging there. Okay. So now when I look at this, I'm going to look at, okay, what are my torques? Well, I have this one is going to be clockwise. This one's going to be clockwise. And this tension is going to pull it counterclockwise. So I have my torque clockwise minus my torque counterclockwise. Okay, and that's the sum of my torque clockwise and counterclockwise. Okay, so I know that my torque clockwise is going to be 150 newtons, and that's going to be equal to 0. So 150 newtons times 1 meter plus 600 newtons times 1.5 meters, because remember, this distance is 1.5 meters. And then minus my tension right at 2 meters. Okay. So then I end up looking at that and I have 150 plus 900 is equal to tension right times 2. Okay, so that's going to end up giving me 1050, and I cut that in half, and I'm going to end up getting 525 newtons is equal to my tension in my right. Okay, that's 525 newtons because I have 1050 divided by 2. Now I need to look at what's my tension in my left. And what I need to use for that is now I need to use my sum of forces. My sum of forces in my y equals 0. And I'm not paying attention to my sum of forces in my x, so I don't even need to look at it. And what are those sums of, what are those forces? Well, the forces are my up forces, which are tension L plus tension R, minus my downward forces, which are 150 minus 600. Okay. And so I have 1050 is equal to tension left plus 525 newtons. Well, right there, I can look at that and go, okay, well, I know 1050 minus 525, so tension left also equals 525 newtons. Okay, and so in this case, so what did we do? We looked at the fact that our sum of our torque equals 0, and we found a pivot point. We identified where our pivot point was going to be, and then we determined what our tension was or what our force was based on where that pivot point was going to be. Okay, then we used that information to determine what our forces were, our linear forces or our translational forces, knowing that the sum of forces is equal to 0. Okay. When I look at this problem, it's a 4-meter long wooden plank is balanced on a fulcrum. Okay. And it is not, that's not placed under its center. The plank has a mass of 15 kilograms, which is uniformly distributed over its length. Where must the fulcrum be located so that a 30 Newton weight placed at the left end of the plank balances it? Okay, so here we have a 30 Newton weight, we have a 15 kilogram plank, and that plank is 4 meters long. And that 30 Newtons, okay, so this is 4 meters, okay? And on the left-hand side, so directly here, we have a 30 Newton weight, okay? And at our 2 meter point, we have 15 times 9.8, which is equal to 147 newtons, okay? And then we need to figure out, where does our fulcrum need to be? Our fulcrum is our pivot point. So I'm going to go ahead and put this right here, put my pivot point right there. And I'm not 100% sure what that's going to be, okay? So here I have my sum of torque. Remember, that's the first thing we need to consider, is equal to 0. Okay, and so what are my torques going to be? Well, I have the torque of the wood plank, and I have the torque of my 30 Newton weight. Okay, and because they're going to be going different directions. This one is going to be causing it to go clockwise. This one is going to cause it to go counterclockwise. And that's why we know that the fulcrum, the pivot point, has to be in between the center and that 30 Newton mass, because we need something to cause it to counterbalance that, that torque that's going to be there. Okay, so we know that 0 is equal to 147 newtons times, this is going to be x, and let's make this 2 minus x. Okay, so our distance is going to be 2 minus x. Okay, and then minus 30 newtons times x. So we get 30x is equal to 294 minus 147x. Okay, and again, we're trying to figure out where the fulcrum must be located. Okay, and so our x value is going to be the distance from the left-hand side. So we figure this out, we get 177x equals 294. So we know that that is going to, x is going to be 1.66 meters from the left end. Okay. Looking at this next problem right here, we're looking at a sign that we're hanging from say a building, like you saw in that very first slide for today. So we have a 300 Newton uniform rectangular sign, 4 meters wide, is suspended from a horizontal 5 meter long rod. Okay, so here this is going to be 2.5 meters. And then that's going to end up giving me the weight of our rod, okay? So the force of gravity of our rod, okay? And then we have our 4 meter wide sign. So the 4 meter wide sign, that weight is going to go here. And so we're going to actually extend it up here. This is the force of gravity of the sign. Okay, and that right there, it says the weight of the rod is 80 newtons. The left end of the rod is supported by a hinge, and the right end is supported by a thin cable, making a 20-degree angle with the horizontal as shown in the picture. Find the tension in the cable and the horizontal and vertical components of the force exerted from the left end of the rod. So here, because we see this lines up here, we know that this distance is going to be 3 meters. So it's going to be 3 meters for the force of gravity for the sine specifically. Okay, so we have that, and then we also have our tension force, and then we have our force X of our hinge, or force Y of our hinge, sorry, and our force X of our hinge. Okay, so those are the different forces that we're going to have. Now, if you were really drawing a free body diagram of this situation, you would be looking at, we have our force of gravity of our rod, our force of gravity of our sine, our force of our hinge, and then we have a tension force. Okay, so looking at that, we have a lot of different things that we need to solve. So we need to start with our torque. And we know that our torque clockwise is equal to our torque counterclockwise. Okay, and the reason that we know that is because we have our sum of torque equals 0 because it is in static equilibrium. Okay, so what are our clockwise torques? And what is our pivot point going to be? Okay, I'm going to set my pivot point at my hinge right here. Okay, so if I set my pivot point at my hinge, this is not going to add to my torque. Okay, so I have my clockwise torque is going to be my force of gravity of my rod times the distance of my rod, which is 2.5, plus the force of gravity of my sine times, that's going to be 3 meters. And again, the reason that that's 3 meters is because this is 1 meter and this whole sine is 4 meters, so 2 meters to the center of mass for that. Okay, and that's equal to our torque from our tension. But the tension force that we're looking at for our torque is only our tension in our y direction, and then times our 5 meters. Okay, and the reason it's only the tension in the y direction is because, remember, we're looking at torque is equal to the perpendicular radius times the force. Okay, and so when I look at that, my force of gravity is going to be, for my rod, is going to be 5. Our rod is 80. So 80 times 2.5 plus 300 times 3 equals tension Y, and I'm going to divide both sides by 5. So I'm going to end up getting that my tension in my Y direction is going to be 643 newtons. So I'm going to end up getting my tension Y. I know that my tension Y is going to be equal to my tension sine 20. Okay, so I figure out that my tension in this case, because I'm going to divide by sine 20, is going to be equal to 643 newtons. Okay, now the next thing that I need to do is I need to figure out what my force of my hinge is in my X and my force in my Y. Well, if I look at my sum of my forces in my X, that's equal to 0, and sum of forces in my Y equals 0. And in my X, it's going to be really easy because my sum of forces in my X are going to be equal to the force of my hinge, so the force of X of my hinge minus the tension X. So I know that the force of X of my hinge is equal to my tension cosine 20. Okay, so when I go ahead and plug in 643 there, I end up getting force X of my hinge is equal to 643 cosine 20, which is 604 newtons. Now, when I look at my sum of my forces in my y, what are those going to be equal to? Well, I have my force of my hinge in my y plus my tension in my y. So I have tension in my y as tension sine 20 minus my 80 minus my 300. So I end up getting my force in my hinge in my y direction is 160 newtons. And then finally, we have one last question. It's a 2,000 Newton steel rod that is 5 meters long, is placed to the corner between the floor and a wall and balanced at an angle using a cord attached to the wall. The rod is balanced such that its top is 2.38 meters away from the wall. So we have 2.38 meters away. Okay. And the cord is 40 centimeters long. So 0.4 meters. And is attached to the wall at a height of 75 centimeters above the floor. The diagram to the right shows the situation if the lower end of the rod does not slip from the corner. What is the tension in the cord? So again, we know that our clockwise torque is equal to our counterclockwise torque. And what are the things that are causing the board to spin? Okay, well, we have the tension of the cord is going to cause it to go this way. This is the tension of the cord. And then the board, the weight of the board is going to cause it to go that way, is going to cause it to go counterclockwise. Okay, so we end up having our perpendicular radius for our tension times our tension is equal to our perpendicular radius for our steel rod times the weight of our steel rod. So here we have 0.75 meters from our pivot point, because this is going to be our pivot point, times tension is equal to 1.19 times our weight, which is 2,000 newtons. And that 1.19 comes from the center of where this mass is going to end up being pulling down, because you've got that 2.38 meters. So then I end up getting that my tension in this situation is 3,173 newtons. So hopefully those examples will help you as you're going through your assignment for today. If not, please go ahead and reach out if you have any questions.